Okay.
So welcome back for the final lecture of Massimiliano's mini course, also the final lecture for this year's OOPS. So please.
Yes. So thanks again for this opportunity. Uh, so let's just start. This is my last lecture. I think I have to somehow reduce. I think I will not have time to discuss like elliptic equation. I think it would require a mini course on itself, especially because it involves strange concepts like supersymmetry. So let me just recap rapidly what we did. So in the first lecture, I introduced the setting and the kind of object I want to look at, and somehow also the perspective, and discuss this idea that stochastic quantization is actually a kind of stochastic analysis of Euclidean quantum field. And actually yesterday, Omer asked a question which somehow stressed this point, because he asked the question, okay, what about different kind of equation? Okay, different kind of equation have the same invariant measure. So what's going on there? And actually this stress, somehow I can turn it around this question and say, yeah, you can use different kind of equation. I discussed it in the first lecture, different even methods to implement to really have a way to identify a measure as an invariant measure or as some other object related. So enlarge your probabilistic objects, add more randomness in your system. Actually, that's really the idea. You add more randomness, you add an external source of randomness, and then you project it down via some very non-linear map. And then every equation gives the same measure. So every method has advantage and disadvantage. I also said that I don't really see major advantage of one method on another. More or less, the kind of problem, the major problem I see in one method appears in other methods, more or less in the same way. So they are not clearly an advantage problem. People are used to this parabolic setting where you have time, but I stress that you can use the elliptic equation, and also you can use the variational method, and more or less each of them give the same kind of information at the end of the day. So somehow maybe reflecting on the question of Omar the yesterday actually, this is another maybe indication that all these different methods are just different version of a same underlying mathematical structure. Okay, so when you have three methods and they all give the same result, and more or less you can really relate one to the other. Okay, if you start to read the paper, you can relate the various things. They are not alien one to each other. Then you start to think that there could be, maybe there is no formalization, but certainly the mathematics involved is very much unified. Okay, I cannot name it yet, but somehow this is the feeling I have. And then what we did, we really get hand dirty looking at how you really walk with this kind of thing, because unless you walk, you don't see the advantage or somehow you don't see the novelty in this methods. Okay, and I proved to you, essentially I gave you more or less a fairly complete sketch of the proof of the infinite volume limit, and also uniqueness in certain easy condition, if you want, so somehow high temperature regime, for a finite lattice spacing, okay? And so my plan for today is somehow to complete this picture and also take the epsilon going to zero limit, and also discuss properties of the measure you obtain as soon as you take both limits, okay? So that's the goal of today, is renormalization and small scale limit and properties. So let's go on, and I want to disentangle the two problems, because they are really two different problems which interact, but they don't somehow disturb each other very much. So the L going to infinity limit and the epsilon going to zero limit are really different. So let's, for the moment, stick to L finite. I will not try to make my estimate uniform in L. Just I want to have estimate which pass to the limit as epsilon is going to 0. Okay, all this matter is about estimate. Okay, because the problem is have tightness of a family of measure. Okay, so you really, the only thing you need is estimate, and then they come along with some other property, and these I will discuss later. But so I remind you the setting. The setting is that I was looking to this shifted stochastic quantization equation. Yt is this dynamic Gaussian free field, and then Zt is what you have to add to it to make the full interacting field. So somehow Zt contain information about this interaction and the non-Gaussianity of the problem. Now my focus is about taking epsilon going to 0. So I'm on the lattice. I didn't wrote down everything, but just imagine that I'm on the lattice. This equation is just a system of ODE on a finite lattice, but letting become finer and finer. And there will be problems. So you start to see this problem, for example, as you try to compute the size of the random field, the Gaussian random field at a given point. Okay, I'm on a point on the lattice. I compute just the size of, so the variance of this random field, its center in its Gaussian. So more or less this tell me everything. And okay, this is an explicit computation because you know the covariance on the lattice. So this is somehow the propagator in Fourier space on the lattice. You sum things up. So as epsilon is going to 0, the lattice become finer and finer. So when you go in Fourier space, you have also a finite number of Fourier modes, but they become more and more. Okay, because the number of degree of freedom, of course, increases. So you have you have to sum over this this lattice of size 1, but very large size in the dimension. And the function you have to sum its decay like 1 over k squared, because this is the propagator of the Gaussian free field. Okay, it's the inverse of the Laplacian. And so you see that you have a problem when the dimension is larger or equal than 2. Okay, this function is not summable at infinity. And in dimension 1, there is no problem, function is summable, but essentially the object because you already know somehow that the Gaussian free field in dimension 1 is essentially a Brownian motion, and the Brownian motion, it exists. Okay, when you take lattice spacing going to 0, the random walk converges to a Brownian motion, and it exists. No problem there. But in dimension 2 and higher, you see that there is a problem. Maybe you already know, if you're familiar with the Gaussian free field dimension 2, you know that it's not a function, it's only a distribution. But that's in our approach, that's how this appear. That is, we have estimates, which I didn't go back to my last lecture, but if you look the last lecture, essentially our estimate rely on like L4 estimate of the Gaussian free field. Okay, and this tells you that the variance of the Gaussian free field diverges. So therefore, norm, there is no reason that stay bounded. Because therefore norm is really a pointwise norm, and here pointwise this thing diverges, and you can imagine that this is a problem for us. And this is hint that this is not converging to a function. Okay, in 2 dimension the divergence is logarithmic. Sorry, in higher dimension the divergence is polynomial in epsilon, but essentially we have both problem. And if you go back in your estimates of yesterday and you try to look at them to quantify the dependence on epsilon, you will see that they will not be bounded for this reason. So we need better estimates. And the problem is that we cannot treat y as a function, okay, as a pointwise well-defined function. Okay, the pointwise fluctuation of y become unbounded as the lattice spacing becomes smaller and smaller. So we need a smarter way to proceed. In particular, we need to control y in negative regularity space. Okay, y will be really controlled only as a distribution. So now the idea is that we need some way to analyze distribution, which is nice on the lattice and pass well to the continuum limit. And this tool it's provided is not the unique tool, but somehow it's a very convenient tool by Littlewood-Paley decomposition. So I have a question in the chat. Missing an inverse of the Laplacian. So let's see if have it.
That was on the previous page.
Here, no? Ah, yeah, you're right, of course. Yeah, yeah. Thank you, David. Yeah, so this is really, so this is is this the Fourier transform of this propagator computed at one given point. Okay, so you don't have the Fourier factor. Thanks. Okay, so let me go back to this literal Pauli decomposition. So the point, it's very easy, and you take a function. I explain in Fourier space, but essentially it's some kind of smart way to decompose a function in pieces which are well behaved. And what you do, well, you compute the Fourier transform, and instead of going back and summing, so if you don't put anything, this go back to the function, but actually you just single out a subset of the modes. Okay, so you don't sum over all the possible modes. On the lattice, there are finitely many, but they can become unbounded. So you don't sum over all them. You just sum over a subset, and you choose this subset with a function rho, which looks like this middle function here, like actually more or less this function here. Actually, let me write. So, sorry. This is, let's say, so this is rho k, and then you have other function. This is rho. This is you multiply with factors, so this is rho k minus 1, and then you have rho k minus 2 k. Okay, and then you can imagine, and the point is that you can choose this function rho k, so that when you sum all together and you sum, of course, what is missing here near the origin, then you get 1. Okay, so you have a nice partition of unity in Fourier space, which is smooth, which is each piece is compactly supported in an annulus, because I'm looking at the modulus. So okay, you can write it, you can be smarter than me and write it appropriately, but essentially I just wanted to give you an indication how does it work. Okay, so you just do a Fourier decomposition, a partition of unity, which is like radially symmetric for simplicity, and where each piece has a wave vector with a given size, 2 to the I. Okay, so delta I of f is a function which is compactly supported in Fourier space, which means that it's holomorphic as a function of x, and then essentially the fact that these functions are on a lattice or not only shows up in my analysis on the fact that these blocks, which are called literal Pauli blocks, I'm used to denote them as delta I of f because I think of them as blocks, and because there is a relation with martingale theory. So you can think these are increments of a martingale, but an analytic martingale in some sense. So, but this somehow collide with the notation with the Laplacian. I'm sorry for that. Usually there should be no problem, but if you are confused, just ask. Okay, so lambda for me is either the Laplacian or the literal Pauli blocks, and when it's a literal Pauli block, usually you have index I or an integer index. Okay. And essentially, you have to think in your mind that what happens when you're on a lattice is just this sum, it's finite up to a given number, which is the logarithm of the lattice spacing, of the inverse lattice spacing. And that's the only thing which is different from this lattice to the full space. Okay, there is no other difference from the point of view of this theory. And actually, every estimate, if you can do estimate in the full space, you can usually do on the lattice. Okay, so that's very nice. And with these blocks, then you can somehow start to understand the behavior of distribution, because whatever function you have, whatever distribution, you can always decompose in these blocks, and these blocks will be nice. Okay, so the regularity of the distribution will become just a problem of the summability of this series. Okay, but not on the regularity of each piece. Each piece is infinity for any distribution. Any Schwarz function distribution, tempered distribution, and yeah. So let's just compute this kind of things, So now instead of computing the oscillation of the Gaussian free field, I take a block of the Gaussian free field, block of frequency 2 to the I with this little Pauli projector, and I compute the variance of this function. Okay, so this field now, it's smooth. It's a smooth Gaussian field, and you see that by this computation, since you have now restricted the sum over finitely many modes, essentially, the sum is finite. Okay, and it has a size. The size is important, which either in 2 dimensions is just uniform. Okay, every block has the same size. In 3 and higher dimension, the block size grow polynomially like 2 to the I and with some power. Okay. And then this says to you, essentially, this indicates that this little Pauli block function, random function, they fluctuate with a prescribed size, which now does not depend anymore on epsilon. And then you can take the limit as epsilon goes to infinity, and essentially you can construct the Gaussian free field and even the dynamic Gaussian free field as a sum of infinity Gaussian fields. Okay, which is very nice property to have. And then you somehow use the size to define spaces, okay, in the sense that, okay, given if you give me a distribution, what I do is that I compute the blocks of this distribution, I compute certain spatial size of this block, maybe using a LP norm, and then I compute certain size of the sequence of number I obtain. So the sequence of number is just a function of I integer from -1 to infinity. And then you use small LQ spaces, and these define Bezos spaces. Okay, Bezos spaces depend on 3 index, the spatial summability, the summability in the scale index, and the regularity, which is this multiplication factor in the scale index. The easiest to understand are the spaces where you have infinity, infinity, because the idea is that the norm really corresponds to the smallest constant with which you can write this bound, okay, for every block. Okay, so in L infinity, so I will write C alpha for the B alpha infinity, infinity space. And this means just that the block have a certain polynomial behavior in alpha, in the block number, okay? And then another notable space is that when both your index are 2, because little Pauli theory is nicely built so that these spaces really correspond isometrically to Sobolev spaces. Okay, this is just because of Plancherel. You use Plancherel formula and you realize that really the 2 norms are equivalent. And these are the fractional Sobolev spaces defined in this context with the L2 norm of the fractional of the Laplace operator. Okay, you can do in Fourier space, for example. Here we are on the periodic setting, so you can use Plancherel formula and the fact that Laplacian is a multiplier and do it in Fourier space. Okay, so this is the kind of analytic setting I want to use. Okay, we will use Bezos spaces, and you have only to know, essentially, all you have to know or really understand vaguely about Bezos spaces to follow are the property I wrote. They are Banach subspaces of in S prime. When alpha is positive, these are really space of more or less regular functions, but essentially functions. Okay, you can evaluate this distribution in points. When alpha is negative, they're just distributions. Okay, for example, if you want to have an understanding, the delta function in 0 is a Bezos distribution, and it belongs to C minus D. And it belongs also to, for example, it belongs to B11, okay? So you see the regularity and the integrability. You see that in general, you cannot expect, so let me write, so it's a distribution. So if you compute in infinity, infinity, yeah, so you see when alpha is 0, you don't know if it's a function, okay, because that's not enough information usually. but in B11, so this is almost a measure. So essentially in B11, you don't have divergence. Sorry, B1 infinity, actually. I'm not sure if it's not in B11. Actually. Yeah, so you have this kind of things. Okay, you can play the game to try to compute the base of regularity of the object you like, but the only object we are interested in is the Gaussian free field. And then you can prove that essentially the Gaussian free field lives in integrability is infinity, and regularity is d minus 2 over 2 minus n small k. Okay, so in 2 dimensions, this is just an arbitrary negative number. In more than 2 dimensions, these start to be negative, fairly substantially negative, but essentially that's the regularity. Integrability, you can take infinity. And then you can prove that the dynamic object as a function of its time variable, it's continuous in time with value in this space, okay? And this is uniform in epsilon, and the limiting object is the same. So keep in mind that y epsilon has this regularity, okay? We will measure it in this C infinity, so C holder base of spaces, which are spaces where the summability is infinity and the regularity is alpha. Note that when d equal 1, this is really, did I got it wrong? Yeah, I got it wrong, of course, this is minus. So when d equal 1, this is really the regularity of the Brownian motion, okay? These spaces when alpha is positive correspond to usual order spaces. And then the last thing I want to mention, I wrote it briefly here, but essentially the idea is that when you take product of base of, so base of spaces have a nice nonlinear theory, very easy somehow. When you take product of base of function, it gives you another base of function with the summability you expect from all their inequalities and the regularity which is given by the Walsh regularity, provided the sum of regularities is positive, okay? So this is the important fact you have to remind. This is natural. When you multiply two objects, if they are positive regularities, there is no problem. If one of them has negative regularity, the other one has to have a sufficiently high positive regularity and to compensate for the negative regularity. Okay, so that's all you have to know. And then the summability has the usual behavior that has some ability when you take the product according to all there is inequality. Okay, so for example, you can take product of B11 function with B infinity infinity, and you will be in B11 if I didn't got it wrong. Okay, but of course you can take B22 with B22, but you will only be in B11. Okay, you will not be better than that. Okay, so this just to summarize what I need from Bezos spaces, and why I need them is that just because, I mean, why they are a good setting is because my noise, my random object will, I can measure my random object in these spaces. Okay. Then, okay, so let's see what happens to the random object. Well, there is a theorem which somehow is stated as a theorem because it's easy to do that, but it's not really totally spelled out. But let's say the moral is that, okay, y of t epsilon, so the Gaussian free, the regularized Gaussian free field will converge to a limiting object, which is the continuous Gaussian free field, which is a distribution in dimension bigger or equal than 2. And what happens to nonlinear functions? So I will consider only the square and the cube. And what happens is that the square will not converge, it will diverge to infinity, and you have to compensate for this divergence by subtracting some diverging constant, which could be chosen to be the mean of the Gaussian free field of the square, for example. And then when you subtract this diverging constant, the residual object, which is the renormalized square, converging low in a space of functions which are continuous in time, and in in a space of regularity, you see negative regularity. So from now on, I will fix alpha to be this number, okay? And k, some small fixed quantity. Yeah, there is a question. Is there a question? I heard something. Okay, so alpha is negative, but think about two dimension. This is really a very small negative number, okay? So in two dimension, you can have this convergence in any space of arbitrary small negative regularity, essentially, if you choose k accordingly, okay? But let's say if I choose C alpha for the convergence of y, then it's natural to choose C2 alpha for the convergence of y square, and then you can prove that if you subtract using the same constant, 3 times the same constant times y, so there is a similar subtraction procedure for the cube, which give you a well-defined limit, which you call the renormalized cube. And the important point for us is that the same constant work here as work for the cube. Okay, that's the important thing. So you can renormalize the square and the cube with the same constant with a different coefficient. Okay, it's not that you are subtracting the same quantities, that you are subtracting another diverging quantity. This quantity is diverging more or less in the same way. Has to diverge, okay? And this is, and when you choose the constant really to be the expectation of the square, this is called weak ordering, but of course, you can choose any other constant which diverge more or less in the same way, okay? Plus smaller order term which are not diverging, then everything would be fine. Okay, so these square and cube are not uniquely defined because you have to make a choice for this constant. There is no unique choice. You can make the choice to say this is center, I want this to be center, and then this define the weak ordered square. And for the cube, you have a similar way to provide this normalization in an intrinsic way by saying this has to be orthogonal to lower order chaoses. But okay, I don't want to enter into this point. Just to say that you can choose the constant that these two objects converge, and what is important for me analytically is that these objects are uniformly controlled in some probabilistic way in an analytic space of this kind. Okay, so you have to think that for any, you can compute at a given time, dependence on time is continuous, but dependence on space is only in these Bezo spaces of negative regularity. And then I go back to my equation, and I look better what is the nonlinear term in my equation, because what is a bit magic is that, remember that I still had this parameter beta, which I kept, so sorry, I have a question in the chat, so I understand. Yeah, so there were a question in the chat which was asking, rightly, okay, I understand this is maybe to control the variance. Actually, it's not, this is the reason, but the question was, okay, maybe I understand why I need the square, but why I need the cube. And then let me just go on the next slide, because the answer, so the question is correct. So why you are interested in these objects. For the moment, I just want you to get into your mind this idea that the higher power of, so the Gaussian free field converges as a distribution, and you can make sense of the power of the Gaussian free field by this renormalization procedure, okay? And if you don't renormalize, they don't converge. So this make appear renormalization in the first place. Why you need it? Well, if you go back, so let me go back in my slides, because my problem was to control the limit of this equation. Well, I have to look into the nonlinear part of this equation to see what are really the problem in the convergence. And when you write down the nonlinear part, okay, this is just my computation, you see that, well, you have a problem, okay? The problem is here in your face, okay? You have these powers of y, and you know already that these powers of y, they don't converge, okay? So even before studying the equation, you have a problem in the coefficients of the equation. So what you have to do is exploit the fact that you can choose this parameter beta, which I left free, really to make appear this constant, C epsilon, which then magically give you back the renormalized cube here and the renormalized square here, okay? You have to make this computation yourself, but if you put beta equal this, plus maybe a beta prime, which I leave open, but in the following, you can take beta prime to be 0, just to, I wrote it down just to stress that the choice is not unique. There is a choice to be made here. So the renormalization gives you a non-canonical equation, but that's fine. But the important thing is that it make appear the renormalized square and the renormalized cube. Okay, again, I'm on a lattice, so everything depends on epsilon. I didn't write it down, but the point is that now this object, they don't pass to the limit, but this object now can pass to the limit. Okay, but we already know that they pass to the limit in a negative regularity space. Okay, so if you remember how we did a priori estimate, we multiplied the equation with Z and then we estimated. Now we have to keep in mind that when we estimate things like that, so this is the, I wrote an integral, but it's really a sum, okay, just to have somehow some notation which hints to the limit. Okay, so you will have the cube, then you multiply the cube with Z to compute your a priori bounds, and then you will have to deal with a quantity like this. And what we did for the in the yesterday lecture is that we just use order inequality and we estimate with the cube square of both quantity with the 4 power of both quantities. But here you cannot do, because you know that Y does not converge in LP spaces, converge only in these very negative subspaces. But here it helps you, that is, you have somehow duality theory for Bezoff spaces. So this is like a duality between two objects. So you can estimate one of them in a negative regularity space, provided you estimate the other in a positive regularity space. And since one is estimated in L infinity, the other one has to be estimated in L1. Okay, not much surprise. You can guess what are the, and this is just duality, a duality relation in Bezoff spaces, and then you just have to make, so this is not very much a surprise. If you know a bit of analysis, you could expect that this duality is old, and they hold for Bezoff spaces. And then what requires just a bit of work is that you have to, you see, this norm, these norm are good objects. Okay, I can even write it in green because somehow they are nice objects. So let me write it in maybe in dark green. I don't like this light green, but okay. So these are good objects. So we have to think as a good objects then. Okay, so green. All right. What is still not good is, okay, how, so these objects are good in the sense that I will control at the end. They will be part of my known object as far as the a priori estimate are concerned. So I will not look at them further because they will be handled probabilistically. I already motivated to you that the cube converge in this space, so I expect that this norm to be finite, essentially, uniformly in epsilon. What is still needs some work are these norms. And then you have really to do a bit of work of analysis, but just trust me that by doing some Young inequality, some interpolation theory, you can control these norms with the H1 norm of Z and the L2 norm of Z on the L4 norm of Z. Okay, that's natural somehow because the L4 norm give you integrability. The H1 norm, this is the H1 norm, give you regularity. You need certainly less than 1 degree of regularity. And you see that you need integrability less than 4, okay? Because for the most difficult term actually to control is this one, because you see it's already Z to the cube in a L1 space. So you need at least L3, and then you need also some regularity. So you have to interpolate L4 with L2, because in the L2 you have the regularity. And this is more or less among all these estimates, this is the trickiest one, but it's just a theorem about control of interpolation. Okay, theory is meaning that this space can be bounded by controlling these two norms. Okay, and the point is that I can put a small constant in front of these two norms, because in the Young inequality I can always, when I split this product in a sum, I can always put a large factor on this product, I don't care. So this term is actually diverging with delta, and a small constant here because I need to reabsorb these terms. Okay, this is like in the a priori estimate. Okay, does not change. The only thing that changes is that you have to use Bezos theory to make appear a negative regularity norm here, and you have to renormalize. Otherwise, this object will not converge. Okay, so renormalization and Bezos theory give you the a priori estimate, which then you put into what I explained to you yesterday, and the machinery of a priori estimate and the stationary coupling. Okay, so this I wrote here. So here, you put everything together, but there is nothing new now. Okay, as soon as you add this ingredient, you have the PDE estimates, new PDE estimates, where the good terms are the H2 norm of Z, the L2 norm of Z, the L4 norm of Z, and you have this time derivative of the L2 norm. And then in the right-hand side, you have all the terms that you cannot control, but you don't care because they don't contain the unknown. Okay, so that's the point of these estimates, is to split the dependence on the random coefficient Y and the unknown Z. Okay, the unknown, you don't know it, you want it to be handled by the PDE estimate, and the known object, you know it, so you want to handle it otherwise. And then you just put all these norms in a term which I call Q, which depend only on these renormalized powers. And then you use a stationary coupling to remove this time derivative. But again, okay, you can use coming down from infinity if you like. That's a choice in my exposition to use the stationary coupling. In this context, work very well. And then you have your a priori estimate, okay, because this disappear, and then this is stationary, so this is really an information about the coupling, and this depends only on the Gaussian free field on the right-hand side, and actually you can prove, so this is the key point, since now you are using these negative regularity norms, you can prove by probabilistic estimate that the expectation of any power of this norm, because this is a Gaussian process, so essentially these powers are all bounded uniformly in epsilon. Okay, so this gives you your a priori estimate in this setting now. Okay, that's the end of the story somehow, because remember that we had constructed a stationary coupling. I write epsilon, but imagine that there is L because we are on a fixed torus. And essentially this estimate tells you that on the second component of the stationary coupling, you can control all this norm. And the first component is the Gaussian free field. Okay, so in the first component, I control a negative regularity norm, like this one. I need some cursivity, okay, for the tightness of the first component. The first component is the Gaussian free field, so I control this norm. The second component is the Z field, so I just control the norm which I have in my a priori bounds. Okay, so I can control these two norms. Sorry for this. Alpha is negative. Okay, remember in my conventions, but I forgot writing this slide. Essentially, you have something like this. Okay, I think this is alpha. Yeah, I put to alpha because you need some tightness. So you have this control, for example. And this is controlled by these quantities, and these quantities depend only on Gaussian free field. You do computation on this right-hand side to determine that this is finite. Okay, it's a Gaussian at this point. It's a Gaussian problem. And then, of course, if you project down to the sum to the measure nu, because remember that the coupling, when you look at the sum of the two coordinates, give you the measure nu. Then this gives you the tightness of the measure nu. Okay, I wrote it here. Maybe I have to. So because somehow you can control this, you can control just the sum of the two norms. Okay, it's not very important how. It's actually quite easy to do that. Okay, so just to say that this gives the tightness. Actually, this is tightness for. Okay, so we have tightness. Okay, we have tightness of the family of couplings in, for example, so So we have tightness, for example, you have to take a space, but could be like C minus C2 alpha, because you have to allow some, so the bound gives tightness in a slightly more irregular space. And here you can, okay, choose H just something a bit less than 1/2, okay, for example, to have tightness in this space. But of course, then the a priori estimate give you that the limit also live in H1, okay, just you don't have tightness in H1, for example, for the second component, okay. And add any limit. Gamma is supported on, this will be important later on, but essentially you have to allow some space for the tightness, and here you can you see that the limit also is supported in L4, something like this, okay, but you can, regularity can be obtained later on. That's not very important, okay. Just the first component is the Gaussian free field, so you don't expect to be better than C alpha. The second component is this perturbation, is the difference between the interacting and the Gaussian theory, and it has some regularity, okay, and it depends what you want to do. This regularity could be good enough or not. Anyway, so this concludes the tightness for epsilon going to 0 at fixed L fixed, okay, because we didn't discuss how my estimate. So what is the problem? Okay, I didn't discuss how this estimate depend on L. Okay, so these estimates are not uniform in L. So this is a constant which depend on L, which is finite but not uniform. Okay, so these constants depend on L. Why they depend on L? Because essentially what you are doing here, actually the norm itself does not depend on L. Sorry, let me say it more appropriate. This norm, it's really that is it's a kind of negative L infinity norm, okay? So it looks at all the space and decide what is the size of my object, because it's L infinity. So let me be precise. So Q does not depend on L. What depends on L is the average of Q, because then, of course, since you're looking at the full space and you're looking at the maximum of some Gaussian functional, when you go very far, you can see something very large, okay? So these estimates are not uniform in L, okay? Estimates not uniform in L. So that's why that's not enough to take the L infinity limit, okay? But we already knew from the lattice, okay? You can imagine that if you don't put weights, all these norms are not bounded on the lattice, okay? It will not make sense, okay? These fields are translation invariant, but you try to measure a L2 norm or L4 norm in the full space, so it's clear this norm cannot exist, okay? So that's clear that this method will not work if you try to take L to infinity, but for epsilon going to 0, it's enough and give you tightness and give you, yeah, so what we do for the L infinity limit, now there is nothing new to do, because you just have to put together what we did yesterday with what we did today. So today we understood what are the appropriate norms to control the noise term, the random terms. Yesterday we understood what are the appropriate norms to control the infinite volume limit, namely we have to put a weight. So we just do the two things together and we cross our fingers and things work, okay? Because then when you test to obtain a priori estimate, so the only thing you have to change essentially is in this equation, when you test, you add your weight. And then, of course, what does it change is that then, of course, in this estimate, you have a weight. So you have to understand if you can do the same kind of reasoning with a weight, and it happens that you can. And so you obtain essentially the same estimates where everywhere you have something, you have also weight. And what you expect naturally to have in the right-hand side is that the Gaussian fields, the renormalized powers, you have to control in negative older spaces, they also have a weight, which is good because these weights are going to zero. So now the behavior at infinity does not play a very important role. And if you understand a bit Gaussian fields, you know that somehow if there is some independence, they grow only logarithmically at infinity. So any polynomial weight will make the job to make this quantity very small at infinity, which what you want because you are measuring an L infinity norm. And what you get out of that is that you get tightness and you have a control of these weighted norms, both for the interacting part and for the Gaussian field. Of course, that was easy. Okay, so that's the only thing you have to do, is that put together all the two things to get tightness both in epsilon and L. And then you can use the higher Stille argument, for example, I explained to you the last time, to prove that actually you have exponential integrability of some weighted norm. So what you have to do, you have to use a weight. You are limited to fourth power because essentially you have this coercive term which behave like the fourth power, and you have to use a negative alpha because somehow here the field is the sum of the Gaussian free field plus the interacting term, so it cannot be better than the Gaussian free field. And now I realize that actually that's wrong because of course for the Gaussian free field you cannot integrate the four norms. So let me write this in the way that makes sense actually. That is, under this measure you can integrate yeah, the second component you can play this game, of course, because for the second component you have the cursivity you need. You cannot do it for the Gaussian part. Yeah. Okay, because of course the Gaussian part will not be able, you will not be able to integrate this fourth power. Yes, so you will have an estimate like this for small eta. Yeah, because somehow the higher Stille argument does not really depend very much on the regularity. Okay, you just have to adapt it to this new setting where when if you want to take the epsilon going to zero limit, you have problem with regularity. Okay, then I think here I was a bit too optimistic. So this somehow ends the kind of work you have to do to prove existence or limits in this case. So I can just state very roughly a theorem of this kind. So now this is the technology which would allow you to prove that, let's say, two dimension, then you take the constant b to be the right constant tuned with the renormalization. B prime, you can just take a fixed constant. And then in this case, your family is tight in the space of distribution. I've been vague here. And then any accumulation point, it's regular, reflection positive, and translation invariant, and satisfy an estimate which is not like this, because of course these include also the Gaussian free field. So let me be not for any, I think in this case you can say for any alpha. Okay, because if you, yeah, let me not be very greedy because I don't really, so let me just say H alpha in a weighted space. So this is again, okay, it's a polynomial weight. So something like this certainly holds. Okay, and more could hold, but you have to use the coupling and the splitting of the interacting field as Gaussian free field plus interaction. Okay, and this essentially can be derived in this form really from this bound on the interacting part and the Gaussian bound. Okay, because for the Gaussian you can certainly integrate exponentially integrate the norm by Fernick's theorem. Okay. Okay, so this is the kind of theorem you can prove. So somehow they go a long way, or they're you see somehow I didn't use very sophisticated technology. I used easy PDE estimate, and essentially the two sophisticated points is the convergence of the stochastic terms and the small work you have to do. Okay, the work you have to do to prove these inequalities, and of course the setting up of Bezoff spaces in the lattice. Okay, that's more, and the fact that somehow weighted spaces work well. Okay, but these are not specific to our problem. Okay, it's just generic property of Bezoff spaces and weighted Bezoff spaces. Okay, so yeah, let me just go back and reason a moment about what I was saying here. I think here I was correct, actually. Let me think, because now I'm a bit confused. I wrote this yesterday. So all this, somehow, what I'm explaining is not really written down. It's written down in different technologies, in different papers. So somehow I'm trying to summarize the knowledge in a way that can be digested. But in particular, this thing is not written down in this way. So let me think again. What I think it's correct. So this has to be checked, but I think actually it's correct. Yeah, let me write in this way so that, okay, so because in the higher steel method, you have to put the full interacting field. So at the end of the day, what you prove, it's really for the coupling and for the full interacting field. So this is about the new measure. So I think it's true. I think it's true in this way. And so as I mentioned, so let me just copy it back, because I think this is true in this way. This is what you expect. So somehow this is what you expect from, yeah. So I was a bit puzzled, but this is what you expect from the measure nu. Okay, the measure nu it certainly give you some regularity, at least the regularity of the Gaussian free field, and give you this decay. So I think if you require the right decay and the right regularity, and you require some locality of this norm, then you can do it certainly for small eta. But okay, take it with a grain of salt, because this is not written down with all the details anywhere. So, but I think it's the correct proof. It's the correct statement. And then this was a nice observation in the paper of Eirer Steele. They do it in 3 dimensions, but essentially as soon as you have this bound with an exponential with a norm of power higher than 2, you already know that the limiting measure is non-Gaussian, okay? Because non-Gaussian measure can integrate powers bigger than 2, okay, for obvious reasons. So this already tells you that the measure nu has to be non-Gaussian, okay? So which is something you have to prove, okay? Because, okay, the limiting measure could be Gaussian. Actually, it's what happened in any accumulation point in dimension bigger than 4, it's Gaussian, and in 4 dimension, it's this recent result of Dominique Copon and Eisenman that it's also hold for certain class of approximation, which include the kind we are doing here. But so in lower dimension, you want to prove that the limit is non-Gaussian. Okay, so this is enough. That's a nice observation. So this is essentially due to our Steele, sorry, in the 3-dimensional case, but apply, of course, also in 2-dimension. And actually, we have more, and I need this more later on. So somehow this method does not just give you an Euclidean quantum field. It gives you an Euclidean quantum field at the end, but with some structure, okay? Because you can carry along this stationary coupling, okay? So you don't have only the Euclidean quantum field. So ZT for some given t, you have all the dynamic of the Euclidean quantum field, and actually you have a coupled dynamic of the Euclidean quantum field with the Gaussian free field, with the dynamic Gaussian free field. Okay, that's somehow I think a very important point to me, because this coupling is very useful in many things, and it's not an information that you can guess from the Gaussian from the interacting measure itself. Okay, so it's useful to carry along this coupling with the construction you are doing. Okay, and then you can look at similar construction in the D3 case in this paper with the Hoffmanova, which I mentioned several times. Okay, so yeah, I think my time is over. I've been, let me maybe, since this is the last lecture, I will take 10 minutes more, maybe just because I want to, I have maybe a few more slides and I want to touch some of the properties. And so this is the construction, okay? And the lecture has been a long way along to arrive at this point, and we have essentially constructed a two-dimensional Euclidean quantum field corresponding to this polynomial interaction, which is called 542. Now you want to study this field. You say, okay, is the accumulation points unique, or I mean, there is more than one. So you ask the question about uniqueness of accumulation points, or you can be even more greedy and ask about uniqueness of this coupling or uniqueness of the dynamics. Okay, there are different kind of uniqueness you can ask, but let's say already uniqueness of these accumulation points is not obvious as far as stochastic quantization is concerned. This is, to me, as far as I understand this, it's an open problem. I don't know how to do it, certainly, and the problem is related to the, so I gave you a recipe to prove uniqueness, which is the obvious one. Somehow, if you are somehow in this field a bit, that is, you do a coupling. Okay, you assume that you have two limiting, you have two sequence which converge to two limiting dynamics. So these limiting dynamics are one copy of Z1 and one copy on Y, and another copy of Z2 and another copy of Y. You can put them on the same probability space. That's not a big issue. You can even couple them. You can put them in the same probability space so that Y is the same. Let's assume that you can do that, because that's not the problem in this, as far as I'm concerned. The problem is that, okay, then you try to do a coupling. You try to prove that, okay, since the Y is the same and the two equations are driven by the same noise and they are stationary, they have to be the same. Or there are more than one solution, essentially. So you compute the difference and you try to write an equation for the difference and estimate it by using these PD techniques. And the problem is, so we did it in the lattice case using convexity. And the problem is that as soon as you renormalize and you subtract an infinite quantity in the renormalization, okay, this infinite quantity, then the potential is non-convex anymore. Okay, it's not even bounded below. Okay, what is the problem? Somehow is well, you look, you remember the method essentially was to just ensure that you are in some way in a region, in a situation where this quantity is bounded below. And now this quantity, which is like the variation of constant or whatever the linearization of your equation, this quantity is not bounded below because the renormalized square can be arbitrarily negative. Okay, so that's the problem. And it's very easy to explain. And for me, it's a very hard open problem. I don't know how to solve it. Even in low temperature, okay, you would like to say that when lambda is small for fixed M, or when M is large, then somehow you should be able to prove using this coupling that somehow the only solution to the stationary solution to this equation is H equals 0. And that does not work. And if you look, okay, how they do in the classic literature, for example, in Gim and Jaffe book for uniqueness, you have two ways. You have correlation inequalities, which use very much the structure, the paramagnetic, the ferromagnetic structure of this problem, or you do cluster expansion, which use somehow that lambda is small. And again, okay, so it's, let me make another remark on this respect. So many papers, so uniqueness in finite volume, you can do it with via Markovian technique, okay? By theory of Markov process, you can prove that on finite volume, essentially there is only one invariant measure for the dynamics. So this is the idea. But this technique does not work in infinite volume. Actually, for me, it's not even clear what does it mean to have a Markovian dynamics in infinite volume, or if this is what you really want to have. So I think the interesting point is really to look at the infinite volume problem and then study the infinite volume problem and maybe uniqueness in this case. Okay, even in the lattice theory, there could be a situation where uniqueness is interesting. Yeah, so I will take 10 minutes since this is the last lecture, just to wrap up and to point out another point. So let me go a bit fast, but I want to point out what it buys to you, stochastic quantization. So I told you that you don't have only the limit measure nu, which is the 542 measure or 1,542 measure. First of all, you don't expect uniqueness everywhere, okay, because you could be in the two phases region, so there could be more than one solution actually, but let's say at least in high temperature you would expect to be able to prove uniqueness, and as I told you, this is an open problem. But you have this coupling, so let's see how to use this coupling. Whether the solution is unique or not, you can have more than one coupling. That's not a problem for me. So let's take one of these accumulation points. It's a coupling of the Gaussian free field and this interacting field. Actually, it's a dynamic coupling, but we will not use it today. It's needed in 3 dimensions, but not in 2. In 2 dimensions, you can use this coupling. And I told you that the coupling is concentrated. So this product measure is concentrated in the first component is just distribution of very small irregularity. And in the second component is this interacting, this perturbation field, which is in H1 and L4, okay, in weighted spaces. And then what you can do with this coupling is the following, okay? If you call phi the random variable, which is the sum of x and psi, where x and psi are random variable chosen according to this coupling, then psi is distributed according to the 542 measure in the full space, nu. Okay, and what you can do, well, I can use a mollification. So theta is a mollifier, theta epsilon is converging to 0. So this is not lattice spacing anymore. The lattice spacing has disappeared. You are in the continuum setting. Phi is a distribution because it's the sum of the distribution of a function. And you can mollify it with a mollifier and then take the cube. And then you can subtract what you did for the Gaussian part. Okay, this is a non-Gaussian process. Okay, phi is a non-Gaussian made of a Gaussian plus something else. But you can make the same procedure. I want to define the cube of psi, so I regularize it because otherwise I cannot multiply. Then I multiply, and then I subtract some quantity, which is the right quantity you need to subtract. Why? Well, look at this quantity. This is now a polynomial function of phi. So you substitute this is the composition of phi, this coupling that you have. So you have a part which only depends on x. You have a part and you have various components. Okay, so the part which only depends on x, you recognize that it's the renormalized cube, and you know it converges as epsilon goes to 0. This is not on the lattice, but more or less the argument and the idea of the proof is the same. It converges to the same renormalized cube, actually. Okay. Yeah, this constant could be different, okay? But okay, there is something you have to handle, but okay, you can choose the constant so that it converges to the same renormalized cube. And here it happens also for the square, and you see that here you have some easy convergence, okay? You have a regular convolution which converges to just the distribution in some negative regularity spaces. Now, you look at the other component, and the other component is a regularization of a sample, a random variable, which is already regular because it lives in this space, okay? So it's a H1, L4, it's a nice function. So this object is very easy to prove that it converges to psi in maybe H1, or maybe I have been a bit greedy here. Maybe you need to have less regular, remove a bit regularity to have the convergence, but it's not very important. Why? Well, because this object converge in a slightly negative regularity space, this object converge in a very good regularity space, and then the theory of products of Bezoff function tells you that the product will converge. And then somehow this is the basic idea to prove that if you write this quantity and if you use this coupling, that it comes out as a byproduct of stochastic quantization, then you can prove that under the measure nu, under any accumulation point, this quantity converge as epsilon going to 0 to a limit, to a new quantity, a random variable that can be written as the renormalized cube of the Gaussian free field plus some other contribution. Okay, this according to, again, to this coupling. Okay. So the main argument is that the coupling allows you to prove this very non-trivial fact, that is the renormalized cube exists under the measure nu, okay, for the interacting field. We already knew that they existed for the Gaussian free field, and this argument proved to you that exists also for the interacting field. In 2 dimensions, it's not a big deal, but essentially the same proof works in 3 dimensions, where the interacting measure is not absolutely continuous with locally, even locally, with respect to the Gaussian free field, and so this fact is less trivial. Okay, but essentially the proof is the same, is in the paper with Hofmanova, which I told you. The proof is slightly more complicated because the cube of the Gaussian free field does not exist in 3 dimensions. So it's a different object that you prove that it exists. But somehow the key idea is this coupling and the decomposition. You can do it. And then I'm interested in this cube because, so let me just, I have maybe 5 minutes. I will use 5 minutes more, sorry. Why it's interesting? Because essentially allows you to pass to the limit in the integration by parts formula. So what is integration by parts formula? Well, it's what I'm saying. So the measure nu, it's very explicit. We already saw. So if you integrate the derivative of a function, you can integrate by parts the derivative and compute the divergence of the measure, and the divergence of the measure, it's really given by this density with respect to the same measure. This is infinite volume, is just integration by parts, okay? You can do in the 2nd year. But the point is that now this is a property of the measure, okay? So you see it's a property which involves 2 quantities related to the measure, okay? So this is interesting to go to the limit, and in the limit, sorry, I used a different notation, but I didn't meant to. The idea is that you see this constant, now this constant is the right constant to have here, and I proved in the previous slide that this object, okay, now you have to do an argument here because this is not the limiting measure, but I hope you believed me, or at least you can check the detail in the paper with Hofmanova, that you can really pass to the limit now in this equation and have it valid in the limit. In the limit, this object will not be a difference of 2 things because this constant will be infinity, but we already understood what more or less will happen is that this object will appear. This is the cube, the renormalized cube, which has an intrinsic also definition as this limit. So somehow you can pass to the limit in this equation. You get an equation in the limit for any accumulation point. So any accumulation point nu will satisfy this integration by parts formula, which makes sense because you see f could be taken as a nice functional, so it can be certainly differentiated in certain directions. And so this formula is a bit formal, but you can make it rigorous, okay? So you differentiate just with respect to testing with some function, okay? Something like this, and then here you have the testing of the right-hand side. That's more or less is what I wrote here. And in the right-hand side, you have easy objects. So you see what you have. Well, okay, let me write the rigorous one. So you differentiate with respect to the testing of phi with respect to a test function f. And then in the right-hand side, since I have anyway noticed that I will need later, it's something like this that appear. That is, phi is a distribution in the limit, but you can test with this test function. So that's make a nice random variable, and also for the cube, it will be a distribution which you test with the test function f, which is local. So this is just a functional which you assume you can integrate. So provided you can integrate this, you can integrate everything. Think about this as a bounded functional. So you have just to prove that this is integrable, but everything makes sense provided you can define the cube. And the cube is well defined essentially because what you do is essentially you define it as a distribution in this sense. Okay, every time you test, you test with the function f, you integrate this regularized square, and then you take the limit and the point of the previous slide, and this limit exists under nu. Okay, this would not exist on the full. You see, this is a probabilistic result related to the measure nu, is that under nu, this limit exists in probability and in some LP in some very nice sense, so that you can make sense of this random variable under nu, and then this random variable appear in the integration by parts formula, and this gives rise to relation between correlation function. Okay, you take this functional to be just a polynomial of the field tested with various test function, and then you can use it to derive what are called Dyson-Schwinger equations. So is the integration by part formula meant to characterize? Okay, so that's a good question. Somehow it's a property of the limiting of any accumulation point. And now I will mention later that that's an open problem as far as I understand to use it to characterize the measure. Okay, so I don't know any non-trivial case in which you can prove it. Maybe David can correct me, but I looked again in Glimme-Jaffe today, and they mentioned integration by part formula. They prove it, so you can look how it's proven with the classical tools. But there is no claim that, and they prove that the measure it's unique. So somehow in Glimme-Jaffe, the proof that they don't prove even that this family is tied. They essentially prove that this family has only one accumulation point. So there is a limit, and this is done by correlation inequalities. And then so this limit satisfies this equation. But what is interesting is the question, which I don't think it's answered in the book or in the literature. I know that give me a measure which satisfies this equation. Does this measure it's unique? Already keep in mind, so that's a very interesting point. So keep in mind that already stating this equation, it's non-trivial because you need the cube. So you cannot just state for any measure on distribution, because maybe any measure on distribution, you cannot define the cube. You have to restrict the class of measure. You can certainly say, let nu be a measure for which this limit exists. Okay, so I can define the cube and I can define the right-hand side. So I have some integrability. And then I can formulate this property. Then the measure, moreover, satisfies this equation for any nice class of test functionals F. Then the question is this measure unique? And as far as I know, I don't have an answer, at least for 542. And I don't know cases, maybe it could exist, but I don't know any answer. And that's an interesting problem I would like to study. Formulated in this way, I don't know any answer. So for me, it's an open problem. Maybe I'm wrong, but if somebody correct me, I would be interested.
I do not know, but it's usually called proving an equation of motion. That would be what you should look under if you want to find out what people have done. And I don't know, I never looked into this, and I agree that it's not in Glimme-Jaffe's book. Okay, yeah, because for me it's a very, I mean, this is the only characterization. Actually, Glimme-Jaffe say so they claim, or they introduce the integration by parts formula, and then they said this is somehow a characterization of the measure nu. Okay, they call actually 542 phases measures which satisfy the integration by part formula, but somehow they don't really discuss this problem. Okay, is any measure satisfying the integration by parts formula 542? And so I can prove, can I prove uniqueness, for example, or can I prove that other properties? Even perturbation theory is not clear to me if you can prove only using integration by parts formula. So this could, maybe this is possible, but okay. Anyway, yeah, so maybe, yeah, so David confirmed a bit that the problem exists, and actually, but it's also pointed out that in the mathematical physics literature, they don't call it integration by part formula. I think they call it either Dyson-Schwinger equation or equation of motion, because this is the Euclidean counterpart of the equation of motion in Minkowski space. Okay, this is used to prove that when you do the Euclidean, when you go back to Minkowski space, this is done actually in the book, I think, of Glimenjaff. It's proven that using this property of the measure nu, when you go back in Minkowski space, then the operators you construct, they satisfy the a nonlinear wave equation. Okay, so somehow this Laplacian become the box operator. This is become the nonlinearity, and by some magic, which I cannot explain because I don't fully understand, this term disappear. Okay, this become the commutation, the equal time commutation relation, which disappear when you compute a certain good quantities. Okay, especially when you compute correlation functions. So you will not see this term. Anyway, so let me end this point with this. I think this will be an open problem. So let me just end up. This is my wrapping up. So I need just 2 slides just to wrap up. So this I will not read because it's what we did. I will not go back. Let me say my goal is really to have this idea to develop a stochastic analysis of Euclidean quantum field and along the lines of these lectures. And then I put some bibliography on recent results. For example, I just discovered that there is this, there are 2 very new papers. The first one is a full construction of the sin H Gordon equation. So when the interaction is sin H using the elliptic, including uniqueness, because in that case, this coupling approach work. So you can look there, how does it work? And then in some range of parameter, okay, not all the parameter. And then there is a recent paper on perturbation theory, which used the integration by part formula for 542. Really appeared like 2 days ago or 3 days ago, I don't know, recently, okay? But this tells you how to use, for example, this integration by parts formula to derive a perturbation theory. So I didn't read it yet, okay, I skimmed over it. I wanted to mention in this lecture. And then I made a list of open problems, which already I discussed in some other talks. And one open problem is what we discussed before. So are these Dyson-Schwinger equation determining the measure? This is free form. This is an open problem for me. Decay of correlation, as I told you, like this is uniqueness, or decay of correlation is the same problem. I think if I can prove uniqueness along the line of this coupling, you can also prove decay of correlation. So maybe it's only through the proof only work in high temperature. I don't know. Grassmann fields. So what happens for fermions? There is some work of myself with Borasi, De Vecchi, and Albeverio, but we don't have renormalization yet for stochastic quantization. And then new, very exciting work on Yang-Mills by Eirer, Zambotti, Chandra, Chevirev, and Shen. It's a large group, but it's a very difficult problem. But again, it's a partial result in the sense that only local theory is there and not the global theory. And so somehow for stochastic quantization, you want also to understand the global theory, so large space or large time if you do parabolic quantization. And this means understand what happens when you have large fluctuations, okay? And in phi 4, this is handled by the 4th order term, which kills everything, or by which give you this coming down from infinity, but in Yang-Mills you don't have it, so it's more subtle what should go on there, and more geometrical somehow. That's why I wrote geometric. Okay, it's related to the geometry of fiber bundles and connection over fiber bundles. And then, yeah, I don't understand very well also can you apply stochastic quantization to model like grad phi, where the interaction depends only on the gradient of the field? So they are called massless because you see the measure is the same whether you translate. So somehow if you translate the field, you get the same measure. So they have an additional symmetry, which somehow it's called massless. And then, okay, other question, more technical, weak universality or proving or using stochastic quantity. Yeah, let me mention this because we discussed triviality, okay? I told you already that it's known that in dimension higher than 4, all these measure nu epsilon L converge only to, if they converge to Gaussian processes. And I would like to have a stochastic quantization proof for that, and I don't know how to do it. So that's an open problem to me. Okay, so this means triviality of models above the critical dimension. Not that is not known, is that I think to understand better the problem, we should understand a stochastic and a quantization proof of that. Okay, so I end my lectures here. Thanks for your attention. I just keep the open problem here. And
could I ask a question?
Yeah, sure. So I finished.
Perhaps for the question, we can all thank Massimiliano for the very interesting talks, and then we can go into some discussions. So thank you.
Yeah.
And I think I will stop the recording, and then we can have.
Yeah. Sometimes interesting things are done in the